How did it all start from scratch? This question is not just about science. It is a deep philosophical puzzle that makes us think about the nature of existence and the origin of the universe. The idea of creating from nothing challenges what we know about the world. It invites us to think about the moment when the universe appeared, bringing with it the particles that would make up everything we see around us. This question goes beyond scientific research and concerns what existence means, what does not exist, and how the universe could arise from it. In this documentary, we explore these questions by looking at the universe through the lens of particle physics and cosmology. Scientists use math and experiments to answer these big questions. But beneath their investigation lies a deeper question. What does it mean that something comes from nothing? How can the laws of physics explain the origin of the universe from a state where there was no space, time, and matter? Particle physics is a science that delves into the world of the very small and studies the fundamental particles that make up the universe and the forces with which they interact. Unlike the familiar objects of our daily lives, which are governed by classical physics, the subatomic realm operates according to the rules of quantum mechanics, revealing a world that is both fascinating and controversial. At the core of particle physics is the effort to understand what the universe is made of and how it works at its most fundamental level. Scientists in this field study particles such as quarks, electrons, and neutrinos, which are the building blocks of atoms, the building blocks of matter itself. These particles are incredibly small, so their properties and behavior challenge our conventional understanding of space and time. One of the most important achievements of particle physics was the development of the Standard Model, a theory that describes fundamental forces other than gravity and the particles that make up the universe. According to the Standard Model, there are four basic forces: an electromagnetic force that causes electric and magnetic effects, the weak nuclear force that plays a role in radioactive decay, the strong nuclear force that binds quarks in the nucleus of an atom, and gravity, which is not yet fully explained by this model, but is known to control the attraction between masses. The Standard Model has been excellent at predicting and explaining particle behavior in countless experiments, but it is not the final word. Scientists are increasingly looking for a more complete theory that would encompass gravity and explain the mysteries of dark matter and dark energy, which make up most of the mass and energy of the universe, but remain elusive. The study of particle physics requires incredibly advanced technology, such as particle accelerators and detectors. These machines accelerate particles to nearly the speed of light and then collide with them, allowing scientists to observe the resulting interactions and the resulting particles. Located near Geneva, Switzerland, the Large Hadron Collider, LHC, is one of the most powerful particle accelerators in the world. The Higgs boson, a particle predicted by the Standard Model to give mass to other particles, was discovered here in 2012. This discovery was a major step forward, filling a major gap in our understanding of particle physics. Despite its complexity, the field of particle physics is driven by a simple and profound question: what is the universe made of? The search for an answer led to groundbreaking discoveries and technologies, including the World Wide Web, which was originally created at CERN, the European Organization for Nuclear Research, to facilitate the sharing of information between scientists. As we delve deeper into the mysteries of the universe, the fascinating intersection of cosmology and particle physics becomes increasingly clear, weaving a complex tapestry that encompasses the vastness of space and the detail of subatomic particles. Cosmology, which studies the origin, structure, and evolution of the universe, finds a surprising partner in particle physics, focusing on the basic elements of matter and the forces that guide their interactions. This synergy opens up new ways of understanding what the universe is made of and how it began and evolved over billions of years. At the core of this intersection is the Big Bang theory, a cornerstone of cosmology that states that the universe began in an incredibly hot and dense state approximately 13.8 billion years ago and has been expanding ever since. Particle physics improves our understanding of this primordial moment by studying the behavior of particles at very high energies, similar to those that would have existed only a fraction of a second after the Big Bang. For example, the conditions of the early universe are recreated on a miniature scale in colossal particle accelerators such as the Large Hadron Collider, allowing scientists to study the reactions that took place in the universe's infancy. One of the most exciting aspects of this intersection is the study of dark matter and dark energy, the mysterious components that together make up about 95% of all the mass and energy of the universe. Although dark matter is thought to consist of particles that do not absorb, reflect, or emit light, making them invisible and detectable only through gravitational effects, dark energy is believed to be responsible for the accelerated expansion of the universe. Particle physicists are looking for particles that can make up dark matter. They use both underground detectors and space-based observatories to look for signs of these elusive particles, while cosmologists incorporate these observations into their models of the overall structure and composition of the universe. Dynamics. In addition, the study of the cosmic microwave background radiation from the remnant of the Big Bang provides a convincing example of the intersection of cosmology and particle physics. This radiation provides a snapshot of the universe when it was only 380,000 years old, before stars and galaxies formed. By analyzing its subtle changes in temperature, scientists can gain insights into the distribution of matter and the nature of the universe's initial conditions, which inform theories of both cosmology and particle physics about the fundamental forces and particles at work during formation of the universe. This interdisciplinary approach not only expands our understanding of the universe, but also challenges and improves theories in both fields. For example, differences in measurements of the Hubble constant, which describes the expansion rate of the universe, suggest that there may be new physics at play that is not currently explained by the standard model of particle physics, or lambda CDM model, the dominant cosmological model. Such anomalies encourage the search for a more unified theory that can reconcile the laws governing the cosmos on the largest scales with the laws governing the smallest particles. Based on research based on the intersection of cosmology and particle physics, it is important to immerse ourselves in the fundamental forces of nature, which are the backbone of the entire cosmos as well as the world of subatomic particles. These forces are like the rulebook of the universe, dictating how everything from galaxies to quarks interact. Understanding these forces provides insight into everything from planetary motion to the stability of matter itself. Gravity is perhaps the best-known force. It is the force that keeps our feet on the ground and controls the movement of the planets, stars, and galaxies. Despite its universal presence, gravity is the weakest of the four forces. However, its influence extends over great distances, holding the universe together. The gravitational force between two objects is determined by their mass and the distance between them, as described in Isaac Newton's law of universal gravitation. Albert Einstein's general relativity later refined our understanding of gravity by describing it as the curvature of space-time around masses. Electromagnetism is the force responsible for almost all phenomena in everyday life beyond the nuclear scale. It works between charged particles like protons and electrons, and is the force behind electricity, magnetism, and light. Electromagnetism is much stronger than gravity at the particle level and is important for the structure of atoms, the chemical bonds between atoms, and the transmission of signals in our bodies. The strong nuclear force, also known as the strong interaction, is the strongest of the four forces, but it operates on a very small scale. It binds protons and neutrons in the nucleus of an atom. Without the strong force, atoms would not exist as they do, because it overcomes the electromagnetic repulsion between the positively charged protons in the nucleus. This force is also responsible for holding quarks together to form protons and neutrons, components of atomic nuclei. The weak nuclear force, or weak interaction, is responsible for radioactive decay and certain types of nuclear reactions, such as those fueled by the sun. It operates at an even shorter range than the strong force and is central to the processes that change one type of subatomic particle into another, such as the conversion of a neutron into a proton, electron, and neutrino. This force plays an essential role in the nuclear fusion reactions that power stars and thus in the synthesis of elements throughout the universe. These fundamental forces of nature are important theories and experiments that connect the vastness of cosmology with the complexity of particle physics. Scientists are trying to develop a unified theory that can coherently explain all four forces within the same framework, a goal that has remained elusive. The search for such a theory, often called the theory of everything, continues to drive much of the research in physics and promises to unlock new mysteries of the universe. We learn about particles, which are considered the building blocks of matter itself. These particles underlie everything we see and touch in our world, from the air we breathe to the stars in the night sky. The standard model of particle physics provides a framework that identifies the smallest constituents of matter and classifies them as quarks, leptons, and carrier particles that transmit fundamental forces. Quarks are incredibly small particles that combine to form protons and neutrons, components of atomic nuclei. There are 6 types or flavors of quarks: up, down, charm, weird, top, and bottom. Quarks are never found in isolation in nature due to a phenomenon called color opening. They are always bound in groups of 2 or 3, forming particles known as mesons and baryons, respectively. Protons are composed of 2 up quarks and 1 down, while neutrons are composed of 2 down quarks and 1 up. The properties and interactions of quarks are determined by the strong nuclear force, the strongest of the 4 fundamental forces, which keeps them locked together in the nucleus. Leptons are another class of fundamental particles, of which the electron is the best-known member. Like quarks, leptons come in 6 flavors: electron, muon, tau, and their corresponding neutrinos: electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons do not experience the strong nuclear force. Electrons orbit the nucleus of an atom and play an important role in chemical reactions and electrical conduction. Neutrinos are elusive particles that hardly interact with matter, which makes them incredibly difficult to detect, although the sun and other nuclear processes produce them in huge quantities. In addition to quarks and leptons, the standard model also includes force-carrying particles known as bosons, which mediate the 4 fundamental forces. Photons carry the electromagnetic force, gluons carry the strong force, W and Z bosons are responsible for the weak force, and the newly confirmed Higgs boson is associated with the Higgs field, which gives particles their mass. Continuing our journey, we enter the Big Bang Theory, a central concept that provides a compelling explanation for the origin of the universe. The theory is a cornerstone of modern cosmology and provides a window into the earliest moments of the universe, suggesting that everything we observe today, from the smallest particles to the largest galaxies, originated from a single, incredibly dense hotspot around 13.8 billion years before. The Big Bang Theory claims that the universe was once a very hot and dense state that rapidly expanded. This expansion is not like an explosion of matter moving outward to fill empty space, but rather an expansion of space itself. Imagine a balloon with dots representing galaxies. As the balloon inflates, the dots move away from each other, illustrating how galaxies move apart as the universe expands. The evidence supporting the Big Bang theory is varied and compelling. One of the most important pieces of evidence is the cosmic microwave background, or CMB, a faint glow permeating the universe that was accidentally discovered by Arno Penzias and Robert Wilson in 1965. This radiation is the afterglow of the Big Bang extended to microwave frequencies, the expansion of the universe. The KMB observations provide insight into the infant universe, allowing scientists to gain information about its early conditions and composition. Another cornerstone of the evidence is the observation of the redshift of galaxies, which shows that the universe continues to expand. That redshift is due to the stretching of light from distant galaxies to longer and redder wavelengths as the space between us and the galaxies expands. Edwin Hubble first observed this phenomenon in 1929 and gave direct evidence that the universe is not static, but dynamic and constantly expanding. In addition, the Big Bang theory explains the relative abundances of the lightest elements in the universe, hydrogen, helium, and lithium, that are observed today. These elements were formed in the first minutes after the Big Bang in a process known as nucleosynthesis, and their proportions match exactly what the theory predicts. Despite its widespread acceptance and strong supporting evidence, the Big Bang theory is not without unsolved questions and mysteries, such as the nature of dark matter and dark energy, which control the energy content of the entire mass of the universe. Hard to stay. Furthermore, the theory does not explain the time before the Big Bang or the fundamental cause of the initial expansion, leaving room for further theoretical and observational research. The Big Bang theory changed our understanding of the origin, structure, and evolution of the universe. It paints a picture of a dynamic universe that emerged from a unique state of unimaginable density and heat that evolved over billions of years into the complex coma we observe today. Immediately after the Big Bang, the universe was a hot and dense sea of energy. The conditions were so extreme that atoms, molecules, and their components could not yet exist as far as we know. Instead, the universe was full of quark-gluon plasma, where quarks, the building blocks of protons and neutrons and gluons, the particles responsible for the strong force that binds quarks together, moved freely in an extremely hot and dense environment. This phase is like a soup made from the main ingredients of the universe, simmering after an explosive birth. As the universe expanded, it began to cool. In the first few microseconds, it cooled enough for quarks to bind together to form protons and neutrons, the nuclei of future atoms. This period, known as the Hadron Age, marked the first step of the universe towards the creation of matter as we know it. Thanks to the additional cooling, protons and neutrons began to form the first nuclei of the universe in the nucleosynthesis phase, a few minutes after the Big Bang. These were mainly the simplest nuclei: hydrogen, which is one proton, deuterium, a stable isotope of hydrogen with one neutron, helium, and a small amount of lithium. The exact proportions of these light elements, predicted by the Big Bang nucleosynthesis theory, match exactly what we observe in the universe today, and strongly support the Big Bang model. However, the universe remained too hot for electrons to bond with these nuclei to form neutral atoms. Only about 380,000 years after the Big Bang, during a period known as recombination, did the universe cool enough for electrons to combine with nuclei, creating the first neutral atoms? This event dramatically changed the structure of the universe and allowed light to travel freely through space for the first time. releasing the cosmic microwave background radiation, a snapshot of the infant universe that provides critical evidence of the larger universe. Bang! The formation of the first neutral atoms marked the transition of the universe from a plasma state to one that could eventually support stars, galaxies, and planets. Gravity began to pull matter together, resulting in the formation of gas clouds that would become the nursery of the first stars. Those first stars synthesized heavier elements in their cores, contributing to the rich chemical diversity we observe in the universe today. Evidence from the Big Bang theory not only supports the view that the universe began as a single, extremely dense and hot state, but also provides insight into the dynamics of the cosmos over billions of years. This evidence is crucial to both the scientific community and the general public, providing a unified observational and analytical account of cosmic evolution. The cosmic microwave background, CMB, is monumental evidence of the Big Bang. Discovered by Arno Penzias and Robert Wilson in 1965, the CMB is a weak light that fills the universe, left behind by the time after the Big Bang. This radiation is the afterglow of the universe's infancy, which cooled to microwave frequencies over billions of years as the universe expanded. CMB measurements from satellites such as COBE, WMAP, and Planck provided a detailed picture of the early universe, showing small temperature fluctuations corresponding to slightly different density ranges. Those fluctuations were the seeds of all the future structures, galaxies, stars, and planets that fill the universe today. The expansion of the universe itself is direct evidence of the Big Bang. In the 1920s, Edwin Hubble made the amazing discovery that galaxies are moving away from us in all directions at a rate proportional to their distance from us. This observation, known as Hubble's law, indicates that the universe is expanding at a constant rate, suggesting that it was once much smaller, hotter, and denser, as predicted by the Big Bang theory. The expansion of the universe is a dynamic manifestation of its explosive origin. The abundance of light elements is another important proof. The Big Bang theory predicts the formation of remnants of hydrogen, helium, and lithium in the first minutes after the Big Bang, in a process called primordial nucleosynthesis. Observations of the relative abundances of these elements in the universe match exactly with the predictions of the Big Bang model, and support the theory that the universe was once in a hot and dense state that favors the formation of these elements. The large-scale structure of the universe, seen through the distribution of galaxies and galaxy areas, supports the Big Bang theory. Galaxies are not randomly distributed in the universe, but form a vast network of filaments and voids. This structure is consistent with the gravitational growth from initially small fluctuations in the density of the early universe predicted by the Big Bang theory. Yours. As we continue our journey, we delve into the concept of quantum fluctuations, a phenomenon deeply rooted in the quantum world that plays a central role in the fabric of the cosmos. Quantum fluctuations are temporary changes in the amount of energy at a point in space dictated by Werner Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be precisely measured simultaneously. This principle is the cornerstone of quantum mechanics and introduces the concept of uncertainty inherent in the quantum plane. In the vacuum of space, what might be thought of as empty quantum fluctuations occur spontaneously as particles and antiparticles jump in and out. These particles, called virtual particles, exist for an incredibly short time before they annihilate each other. Despite their transient nature, they have real effects and can influence the behavior of other particles. For example, quantum fluctuations are thought to cause small changes in the energy levels of electrons in atoms. This effect has been observed and confirmed by experiments. Quantum fluctuations are not just a curious part of quantum mechanics. They are believed to play an important role in the formation of the universe as we know it. During cosmic inflation, the short-lived rapid expansion that occurred a fraction of a second after the Big Bang, these quantum fluctuations were extended to macroscopic scales. This process amplified small variations in the density of the universe, resulting in the large structures we see today, such as galaxies and galaxy areas. The patterns of the cosmic microwave background radiation are a direct consequence of these quantum fluctuations and provide insight into the quantum origins of the universe. At the heart of quantum fluctuations is Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be known precisely at the same time. This principle suggests that even what we think of as a vacuum is actually not empty, but full of virtual particles that pop in and out. These particles are called virtual because they cannot be directly observed. They exist temporarily, borrowing energy from the void to appear for a moment before destroying each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to the creation of real particles. One such scenario occurs near the event horizon of a black hole, a phenomenon called Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole could lead to the formation of particle-particle pairs, where one particle falls into the black hole and the other escapes into space. This process actually creates real particles out of the vacuum, with the black hole losing mass over time as a result of this radiation. Another context in which quantum fluctuations cause particles is during cosmic inflation, the theory that the universe expanded rapidly after the Big Bang. During inflation, quantum fluctuations were extended to macroscopic scales, amplifying their effects. These fluctuations in the density of the early universe were the seeds for the formation of all the large-scale structures we observe today, such as galaxies and galaxy clusters. The increase in quantum fluctuations during inflation means that virtual particles can freeze into real particles, contributing to the matter content of the universe. This process of creating particles from quantum fluctuations highlights the connections between quantum mechanics and cosmology and reveals the quantum basis of cosmic evolution. It illustrates how phenomena on the smallest scale affect the universe on the largest scale, blurring the lines between the void and the tangible, non-existence and existence. Deeper in the quantum realm, the role of energy in the formation of particles is a critical aspect that bridges the gap between the ephemerality of quantum fluctuations and the concrete reality of the universe. Energy plays a central role in the creation of particles and acts as a catalyst that transforms the potential of quantum fluctuations into the material components of the cosmos. This process is based on one of the most famous equations in physics, GeM-C2, proposed by Albert Einstein, according to which energy E and mass m are interchangeable. E is the speed of light. This fundamental principle highlights the deep connection between energy and the creation of particles, illustrating how fluctuations in the quantum vacuum can create matter. What appears to be empty in the vacuum of space is actually a cauldron of energy boiling due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing the formation of particle-particle pairs. Although these pairs usually annihilate each other almost immediately and return the borrowed energy to the vacuum under certain conditions, they can become real particles. The transformation of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For example, in the incredibly high energy conditions after the Big Bang, the universe was a hot, dense soup of energy. As the universe expanded and cooled, some of this energy condensed into particles according to the principles of Einstein's equation. The early universe went through several phases, including the electroweak age and the quark age, during which the fundamental forces of nature split apart. and the building blocks of matter formed and fused into the protons and neutrons that make up the atomic nucleus today. Energy not only drives the creation of particles, but also affects their interactions and the structures they form. For example, the energy released in the nuclear fusion process in the hearts of stars is responsible for synthesizing the heavier elements necessary for life, from carbon to iron. This transformative power of energy, from lighting stars to forming elements, underlines its important role in shaping the cosmos. Navigating the central role of energy in the formation of particles, we find ourselves at the threshold of another fundamental concept that we discussed earlier, Heisenberg's uncertainty principle. This principle is not just a mathematical curiosity, it is a window into the inherent obscurity of the quantum world, and has direct implications for the creation of particles from seemingly empty space. The uncertainty principle, proposed by Werner Heisenberg in 1927, states that it is impossible to know both the exact position and the exact momentum of a particle at the same time. This inherent uncertainty is not due to experimental imperfections, but is a fundamental property of the universe at the quantum level. The uncertainty principle is closely related to the creation of particles, especially in the context of quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum is not empty, but full of virtual particles that constantly appear and disappear. These particles are called virtual because they temporarily exist, borrowing energy from the vacuum due to the limits imposed by the uncertainty principle. The principle allows these variations by allowing violations of temporary energy savings provided that the borrowed energy is quickly repaid, thus avoiding direct detection of violations. This temporary energy loan allows the spontaneous formation of particle-particle pairs. Although these pairs usually destroy each other almost immediately and return the borrowed energy to the void, their short existence is a direct result of the inherent uncertainty of their positions and moments. At the horizon of a black hole, or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of creating particles from a vacuum, facilitated by the uncertainty principle, highlights the crucial role of the principle in the dynamics of the quantum world and the structure of the cosmos.